Hello everyone, my name's Kendall Pitt. I'm going to talk today about the manufacturing classification system. This was designed a few years ago to help identify what the properties are of a particle which you would select to design which way you would then process it for oral solid dosage forms. I am a Senior Technical Director at GSK. I'm also lucky enough to be a visiting professor at the Leicester School of Pharmacy, De Montfort University. The manufacturing classification system was originally designed by a working group of the Academy of Pharmaceutical Sciences in the UK, for which I am grateful for their support. Borrowing from the Oral Biopharmaceutics Classification System, the BCS, to give us a guide as to how we could use a similar sort of concept for particles. We used the concepts from the BCS, the design, to help us proceed. So if you look at the oral BCS, you have along the bottom axis, you have solubility. We have high solubility on the left and low solubility on the right. And you have drug permeability, low at the bottom and high at the top. As you can see, you can then divide the screen into four areas, and then you have high permeability, high solubility compounds, which are easy to get absorbed and processed. And then you have the category 4s, which are low permeability, low solubility. And this you've got like a category of a traffic light whereby green is easy to progress, and then amber not so, and then red is quite difficult. So we looked at this oral biopharmaceutics classification system and a concept of different categories, and then adapted it to use for a manufacturing classification for particles. So why have a manufacturing classification system? So using the concepts of the biopharmaceutics classification system, we're using the properties of the particles to help classify an oral drug product manufacturing system. So this would help you define what particles you need and what are the best processes to put them from. It would also help you to identify in particle engineering what targets you would need for actually giving the ideal API properties. If you had a manufacturing classification system, then it would aid development and subsequent transfer to manufacturing, and it would also provide a common understanding of risk. It also fits with quality by design principles. Now, you'll hear a lot about quality by design in other lectures, but quality by design, in my simple understanding, is it's good science and common sense. What is the science telling you and how you want to put it together? And the other long-term goal of putting together a manufacturing classification system is to provide a framework for regulatory relief so that you could demonstrate the properties of your incoming API and excipients are within established ranges for the process that you've registered. So therefore, you can move readily within that regulation and there would be no issues. So for example, if you look at this slide of what most people regard as good API, it flows well, it compresses well. You can see just by eye that it's smooth and even, and I think it looks quite beautiful and pretty actually. The fact it has a certain nice symmetry about it. If though, for example, you look at this slide of difficult API, you can see in some ways it's quite ugly in the sense that it's sharp bits, there's bits pointing out, and this is what we would find in production we couldn't formulate very well. So the basis of where we went on this is if you could see by eye that these were different, then you could possibly put numbers to this. You could try to get a machine to understand what was different as part of artificial intelligence, telling us what was good and what was a bad material. So what we decided to do was meet together, and in 2013, which is quite a long time ago, we assembled a group of people, that was analysts, that was synthetic chemists, that was formulators, to decide what criteria would they use to identify what's a good or a bad product. So, for example, synthetic chemists were predominantly interested in, could they make it chemically pure? Analysts were interested in, did it have a chromophore? The formulators, though, were interested in, could you make tablets from it? Was it bioavailable, for example? These were all sorts of things. Was it water soluble? These are all things which we put together as working groups to come up with how we could classify the material. So based upon the concepts of 4 classes, we broke the classes down into direct compression, dry granulation, wet granulation, and then other technologies. And the basis of this is that we'd start with a simple process, direct compression, and then dry granulation is obviously where you apply roller compact a product or slug it to actually form a granule. And wet granulation, you're doing more work and more complexity into the system. So, and other technologies are even more complicated than that, such things as spray drying your products or putting them into liquid gels. So, based upon this thought of trying to classify products, if they were easy to handle, they would go into direct compression. If they were complicated, we'd go into wet granulation. We started to think about how you would break apart and classify these compounds. So the assumption is you would actually go for the simplest approach first of all. If it was a nice molecule, easy to handle, nice particle, you do direct compression. If it was complicated, you go for wet granulation. And we also decided that we would build on prior knowledge. That is, there's a lot of information out there about what makes a particular particle good for direct compression, why you would need to think about what to wet granulate a material, for example. So these were all put together in that. And the ultimate aim was to predict from previous experience what your product would need to do, what you need to do with your material. So this is all published. It's in the public domain as a white paper, as a proposal for a drug product manufacturing classification system for oral solid dosage forms. You can Google it and find it on the internet. You might want to Google my name, Kendall Pitt or Gavin Reynolds, as Michael Lean is got quite a number of papers, and also there's a guitarist called Michael Lean. So you'll get a lot of rock hits, but you really just want this paper. So Google those, you will find it quite easily. The key thing about this was it was industry and academic collaboration. We had people from a wide number of areas involved in it, and we rolled out a questionnaire. What did people think was important? And what that questionnaire came back with was that people thought that shape and size were quite important, as was surface area. So if we see how this all put together, you can read the paper in more detail, but this is an interesting example of how we decided that we would start assessing materials. So along the bottom here, we have different properties. So we have dissolution and in vivo on the bottom, flowability, which of course is a mechanical property, something about the drug process form uniformity, and manufacturability, about can you compress it and what the mechanical strength of the tablet is. And this represents 2 different molecules or particles which were examined. And we used the traffic light system. So, for example, this blue line, this blue particle is mainly in the green, easy to process regime, whereas this black line is more of a particle which is a bit more difficult. And the numbers do represent to a certain extent the true values you'd see. So, for example, the higher the permeability, it would be more towards 100 would be better. If it was low, it would be 10 up there. So what would you do with this information? Well, just to give you an idea of how you might want to process the material. The black material, for example, is high risk on flowability. So that might make you decide you wanted to granulate it in some way. So this gives you an idea of how you can process the data and how you can project it. So we said there was a survey which we put out. So people wanted to ask us more questions about Could we use this as a first indicator guide to material and process selection, which is what we said we could do? Are there levels at which you would have to start worrying about your drug? And this revolves about if you've got a low dose drug, say 2 or 3%, you're going to be more concerned about things like segregation rather than a high dose drug where you're probably going to be worried more about things like compression and dissolution. People said it would be helpful in evaluating dossiers for registration, and it would select the pre-set confidence in making the process successful. People quite liked it because it would develop a common language for risk assessment. So people could look at the numbers which were generated, which are in more detail in the paper. So you could have a communication between the formulation group and the manufacturing group as to what the risks. It would also ask about why you wouldn't pick a particular route. Some people may decide they really want to do direct compression, but when you actually looked at the data, it was so you just couldn't do that. Another question people asked is, where would continuous processing fit in this? Now, the continuous processing part was taken off and written as a separate second paper, but by all means, Google the names and you actually find the continuous processing part of that. So one of the things we were keen to sort of think about is, what measurements would you do? How would you go about that? And so from the survey, from our own thoughts, we said, well, first of all, let's look at the size of the particle and the shape. And we also would say we need to have some idea about the distribution of the size. So we look at what the 10% value was, 50%, and the diameter at 90% value would be. We'd also look at the particle shape. We said we start with a simple concept as to how close to a circle is it. We also wanted to look at the mechanical strength, the compression, and said let's standardize at 15% porosity, and let's look at flow. Let's try and measure the flow. We went for the simple test called the Carr index or the compressibility index, which is in the pharmacopoeias. People are also interested in trying to get some idea of the energetics of the particle, how active it was. So we also looked at dynamic vapor absorption on that. When we presented this was to the Federation International of Pharmacists. They called this the friendly list. The aim anyone can do this at minimal cost. This is what anywhere in the world can look at size or shape or mechanical strength or flow. And I'll give examples of that in the next slides. Some of the concepts people said is no product should fail from a predictable reason. That means if you've got the numbers and it tells you the product should work, then use those numbers accordingly. You shouldn't, if it's going to predict it's going to fail, then you should have been able to predict that. And the other thing is if you look at your numbers, what experiments should you then do to help understand the risk of development? Going back to the example of flow again, if you've got poor flow, what experiments are you going to need to do to understand that poor flow, and what might you have to do to adapt your equipment to deal with the flow, or actually what would you do to change the particle properties? This then went on into digital design initiatives where I talked about artificial intelligence and machine learning. And there again, you can Google, adopt, and see that there are some papers out there where we're beginning to look at the shape and size of particles just from a photomicrograph, and then using those to predict flow later on. One set of properties we're clearly going to be interested in is the size and shape. You don't particularly need expensive sizing and shaping equipment to do this. You can do this with a microscope and using your own eyes. This is an example of one which was taken during a USB microscope, whereby an image is taken and then in this case it's just using the microscope software to give you an idea of some of the sizes in that, although you can also use something called ImageJ software as well, which will help you identify it. So from this sort of analysis, you can see what the size is and what the shape is quite readily. Tensile strength I've mentioned once or twice. This takes into account, and is in the pharmacopoeias, the size and shape of the tablet. So In this case, the bigger the tablet, the greater the fracture load you would expect it to have, the breaking load, the tablet hardness. But this equation takes out the impact to size because you're taking your hardness value and you're dividing it by the diameter and the thickness. So you are rather cleverly taking out the impact to size. So what you're going to do with this thing, it gives you a non-dimensionalized value, a value which is independent of the size of your tablet. So the target we're looking for is greater than 2 megapascal. If you make your tablets greater than 2 megapascals, then in production, you're not to run into any issues. I talked about car index and compressibility. In this simple test, you take a measuring cylinder, you fill it with powder, and you tip it end over end to get the bulk volume with a hand over the top of the measuring cylinder, I should say. And then you take that volume reading and then you tap it down. And you tap it and tap it and tap it to see what the minimum volume is. Then the greater the difference, the more pore flowing the material. So this is in a pharmacopoeia. It gives, we'll have similar things. We talk about the amount it drops down, 10%, 15, 20%. And then there's a characterization, excellent, good, fair. Red, you've got problems, and yellow, you've got passable. So anything above about a car index of 25%, you will have problems in production. The reason why the car index gives you such a good measure of flow, because it's really measuring friction. If you've got a lot of friction in the powder, it'll be fluffy and therefore fill this powder up cylinder quite high at the start. And as you tap it, it will then fall back down again. Similarly, the friction will also dictate how your powder will flow. This is an example of where we're measuring the dynamic vaporization of the material. Here we're changing the humidity, so it's 0% at the bottom and 80% on the far side. And up the y-axis, you've got the change in weight. You can do this either with a sophisticated machine called a DVS measurement machine, or you can simply do it with a desiccator jar with saturated solutions of salts at the bottom, and then you put the powder in, weigh it before you put it in, and weigh it again afterwards to see how much moisture it's picked up. And these solutions will have different humidities. What you can see here is that there's clearly, for this particular active material, two different behaviors. These along the bottom here don't pick up a lot of moisture. These pick up slightly more material within that. What was interesting is that when we then made tablets from these, where we're looking at the compaction pressure, this is the force we use to make the tablets, and measure the tensile strength, you'll see that the ones which picked up moisture had a much higher tensile strength. Now, we're not too certain why this is, but it's probably a sign that the more hygroscopic material was, the greater the surface energy of that particular crystal. And that surface energy would also show itself, and in fact, you could make stronger tablets from it. It's a sort of an interesting observation, but it shows what you can do with simple materials. So finally, I'd like to acknowledge that quite a few people helped me in this, the Academy of Pharmaceutical Sciences, Michael Lean from BMS and Gavin Reynolds from AstraZeneca. And there's a whole host of people on the Manufacturing Classification System Working Group who helped make this work. And you can read their names at the back of the paper. So finally, what I'd like to leave you with the thought is, why do we do this? What's the reason that we're thinking about this? We're doing it for the science, but what we're also doing this for is that to bear in mind that there is a patient who is dependent at the end of all our work for their medicines. And so the more easier and more quickly we can make those medicines, then the better and more quickly we can treat those patients. So I'll stop there and say thank you for tuning in, and I wish you ever luck in your future career direction. Thank you.